Okay, so now we're going to discuss prime numbers. And before we introduce the concept of the topic of a prime number, I first want to review a definition that will be useful not only in this clip, but in the next couple to come. We say that a number A is a multiple of another number B if A is equal to B times some C, where C is just some whole number. And we can use the words multiple in conjunction with the words factor and divisor as well. We might also say that B is a factor of A in this case, or B is a divisor of A. So all of these terms kind of refer to the same situation. As just a quick example to illustrate the language, we certainly want to say that 12 is a multiple of 3 because 12 is equal to 3 times some whole number, namely 4. And if we flip this around, we could also say that 3 is a factor of 12. On the other hand, 14 is not a multiple of 4 because there's no whole number that multiplies by 4 to return 14. For this reason, we also say that 4 is not a factor of 14. Okay, so we understand what factors, multiples are. So now let's discuss prime numbers. So I have written the numbers from 2 to 50 on the board. And I want to motivate the discussion of prime numbers with a simple example that uses the concept of multiple. The first thing I'm going to do is I'm going to cross out all of the multiples of 2 in this list. Now again, this list could certainly continue on and on and on. I just kind of ran out of room at 50. So if I cross out all of the multiples of 2, I'm essentially crossing out all of the even numbers besides 2 on this list. And I shouldn't actually, if I'm being precise about this, I'm not crossing out all of the multiples of 2. 2 is certainly a multiple of 2. But what I'm going to do in this little process is I'm going to circle the individual number and then cross out all the remaining multiples. So what I want to do next is just keep doing this with all of the other numbers in this list. I'm going to circle 3 and I'm going to cross out all the other multiples of 3. Now we've already crossed out several multiples of 3, right? 6 is a multiple of 3, but it's also a multiple of 2, so I've already crossed it out. So now I need to just cross out all of the other multiples of 3 that I haven't crossed out yet. 9, 15, 21, 27, 33, 39, and 45. And again, I keep doing this and I'm going to be done pretty soon. I've already crossed out 4, right, because it's a multiple of 2. What about 5? I'm going to circle 5 and I'm going to cross out all the multiples of 5. I've already crossed out a bunch of them, but 25 and 35 still haven't been crossed out yet. I'm going to cross out those multiples. And then I'm going to do the same thing with 7. And the only multiple of 7 that I haven't crossed out yet is going to be 49. And it turns out if I were to keep doing this, so the next number that's not crossed out is 11, there are no multiples of 11 on my list that I haven't crossed out yet. So all of the remaining numbers that haven't been crossed out, I'm going to circle. And what we would like to notice is that each of these numbers that is circled has a specific property that they share. Okay? All of the numbers that are circled have no divisors other than themselves and 1. Right? Because if they had other divisors, they would have been crossed out. For example, all of the multiples of 2 are crossed out. Right? So if any number has a divisor of 2, it's been crossed out. All of the multiples of 3 have been crossed out. So all of the numbers who have a divisor of 3 have been crossed out, and so on and so forth. So each circled number has only 2 divisors, namely the number itself and the number 1. In general, this is a useful characteristic for numbers to have, and this is what we mean when we call a number prime. So this is the definition of a prime number. We say that a number larger than 1, and we'll explain why we exclude 1 here in a minute, but a whole number larger than 1 is prime if its only divisors are 1 and itself. Okay? Primes are often called the building blocks of arithmetic, and we'll see why here in a second. Now, the study of prime numbers is central to the mathematical field of number theory. So there are a lot of people that have been interested in prime numbers for a very long time. In elementary school, however, really the only computation that is done with prime numbers, if at all, because some elementary school curricula don't even deal with prime numbers, but if prime numbers are discussed at this level, they are discussed in the context of prime factorizations. So what we mean by a prime factorization is the following. It turns out, and we will illustrate this through examples, that every whole number greater than 1 has a unique prime factorization. And we'll explain what this means here in a second. But actually, what I've written, every whole number greater than 1 has a unique prime factorization, this is referred to in mathematics as the fundamental theorem of arithmetic. It's a really, really big deal. The proof of this result, again, remember in mathematics, something is true if it has a proof, if we can prove that it's true. The proof of this result is a very upper level proof, which you certainly wouldn't go through in an elementary school class. But you do want to illustrate this uniqueness of prime factorizations through examples. So what do we mean by unique prime factorizations? Well, what we mean is if we take a number greater than 1, say 360, we want to know how can we write 360 as a product of just prime numbers, right? We know how to write 360 as a product. One way of doing it is 36 times 10. But neither 36 or 10 are prime numbers. So what we mean by prime factorizations is how can we write 360 as a product of just prime numbers? Well, factor trees were in vogue when I was in elementary school, and I think they're still used now. They probably will be forever. Factor trees are often used to find prime factorizations of numbers. Okay? Factor trees go a little something like this. We're simply breaking down the number 360 until it is in prime components. So to start, we just need two numbers that multiply to 360. Well, we mentioned 36 and 10 earlier. And if either of these factors are prime, we're going to stop with that factor because prime numbers, remember, don't have any divisors other than themselves and 1, so we can't break them down any further. Neither of these are prime, however. 36 can be written as 6 times 6, and each of these 6's can be written as 2 times 3. Now, 2 and 3 are both prime. They cannot be broken down any farther, so we might circle those. 10 also is not prime. It can be broken down to 2 and 5, but both 2 and 5 are prime. So it looks like we can write 360 as a product of primes as 2 times 2 times 2, 3 factors of 2, 2 factors of 3, and a factor of 5. So 360 can be written as a product of primes as 2 times 2 times 2 times 3 times 3 times 5. Now, hopefully at this stage, you will have a clever student that raises his or her hand and says, well, wait a second. You didn't have to start with the factors 36 and 10 at your first step. There are lots of other combinations of numbers that multiply to get you 360. So the question then is, what happens if we start with a different pair of numbers here? If you start with a different pair of numbers here, could we possibly get different primes coming out of the wash at the end? Well, the uniqueness portion of the fundamental theorem of arithmetic tells us actually no. It doesn't matter what factors you originally start with, the same primes are always going to come out. Now, since you're not going to be proving the details of the fundamental theorem to your students, what you want to do is go through several examples using the same number in different factors at the beginning and showing that the same primes come out. In fact, you could break your students into groups, have one group break it up, break 360 as 36 times 10, have another break it up in different ways and show that in all of your groups, hopefully, you're going to get the same primes coming out. Let's do one more example just to illustrate this. Another way to break down 360 as a product of two numbers might be 4 times 90. 4 times 90 again is certainly 360. And then we can proceed as we did in our last example. 4 is not prime, but it is 2 times 2, and 2 is prime. 90 is not prime, but we can write that as 9 times 10. Neither 9 and 10 are prime, but we can write 9 as 3 times 3 and we can write 10 as 2 times 5. Lo and behold, we have 3 factors of 2, 2 factors of 3, and 1 factor of 5 coming out of the wash. So we see that regardless of how we first factor our number, we are getting the same primes coming out. That's what we mean by unique factorization of primes. Notice, I mentioned a little while earlier that we do not want to allow 1 to be a prime number. If 1 were allowed to be a prime number, we would not have uniqueness of prime factorizations, right? Because I could multiply as many 1s as I like to this factorization to still return 360, but I would get different so-called prime factorizations. Okay, so for that reason, 1 is just out of the discussion. It is not prime, and it's not composite. Composite is the word we use for a number that's greater than 1 that is not prime. So we just say 1 is neither. We don't even discuss it. Now, at the elementary school level, this is really all that's done with prime numbers. Prime factorizations can be used, as we will show on our next clip, to determine greatest common factor and least common multiple of 2 numbers. Least common multiple is used in adding fractions with unlike denominators. However, there are many other interesting elementary school level topics that can be discussed about prime numbers, and I've attached several of these to a PowerPoint that accompanies this clip.